We're going to continue with acceleration. We're going to branch out into equations, how to use them, and now start working in the y direction. Accelerated motion is constant acceleration for our class. We do not have changing acceleration. So we think of acceleration as the rate of change of motion, specifically velocity. Remember that average acceleration, that little straight bar just means average in math. Changing velocity per time. Now, what if the change in velocity continues to happen? You have constant acceleration. Every second, something is happening to your velocity. We're going to solve acceleration problems by determining what you're given, what you need to find, what equation best suits the problem, and then proceeding with math and getting a solution. Our variables, we have to be sure we understand our variables and the units they're measured in. Our equations have an A for acceleration, T or delta T for time, V sub I for initial velocity, V sub F for final velocity. And displacement or change of position is going to be delta X when you're working in the horizontal direction and delta Y in the vertical. You should substitute a Y wherever you see X in the equations. So here we have our constant acceleration equations. Notice that this equation works if you have 3 of the variables and need the 4th one here. However, the change in x, the displacement, is not in this equation. So if you're looking for delta x, this is not going to give it to you. Likewise, in this equation, we don't have v final. So you wouldn't use this equation to get v final. And finally, we need time. This is not a good equation because it doesn't have time in it. So what's our procedure here? This is the same procedure, all the problems. First of all, you're either going to get a picture or a picture will be obvious. You could use a number line. The number line horizontally, clearly to the right is positive, left is negative, like our regular Cartesian coordinates. And likewise, up is positive and down is negative. Any problem that's horizontal, usually these are cars on a level ground, roller skaters, bikes, people walking, delta x is in the equation. If you have anything like balls going up and down in the air, other things getting tossed or jumped, then you have a delta y for the y direction. So we all agree on the positive and negative directions. You fill in your givens. You start with the variable, whatever the letter for the variable is, equals the value, the number that it has in the problem with units. And if it's a vector, you have to give the sign plus or minus. Plus matters. Write the variable that you need to find with a question mark down here, or you could just write the variable. Determine which equation up above will give you what you need. And remember, I provide all the equations on the quiz. There is no memorizing the equations, but you should try to do your best to really get a feel for which equations you use. And we're going to be practicing. And then you substitute all your values carefully with units, and then you do your math and solve, and you will find out that your final answer is a number with a unit, or if it's a vector, a number, a unit, and a sign and direction. Let's talk about things that have motion in the vertical direction only. Vertical means up and down, y-axis direction motion. Now, there are some terms that are new probably to you. Things like free fall object. A free fall object is an object that is only being influenced by gravity. So let's be careful. It's called free fall when it's going downwards and upwards. So as the ball falls down, the only force acting on it is gravity. We ignore air resistance. And likewise, when you throw a ball up in the air and then it comes down, on the way up and on the way down, it's still in free fall. It's harder to understand because we hear the word fall in there, but that's what the meaning is. Only gravity. Free-falling objects do not encounter air resistance, or it's so minimal we can discount it. On Earth, these objects accelerate at a rate of 9.8 meters per second downwards for the whole time the object is in the air. The acceleration is always downwards, negative by convention. Even when the ball is going up, when it stops at the top and as it comes down. Acceleration due to gravity is always downwards. So we're going to have the same motion equations. We're substituting y for the x. So let's plug those in, and we see that here we have v final and v initial, but now they're y direction velocities. We are missing delta y in that equation. In this equation, we have a displacement in the y direction, delta y. The v initial is a y direction initial velocity. A is the acceleration due to gravity, 9.8 meters per second squared, and since it points downward, it's negative. Again, these are velocities in the y direction. Delta y is a displacement in the y direction, and we're missing the letter t, so don't use this for time. See, here our number line is now the vertical part. Same procedure. Draw a picture, choose a location as a 0 reference point, assign positive and negative directions, assign up as positive, down as negative, and of course have your vertical constant acceleration be that of gravity. A acceleration equals negative g, which equals negative of the 9.8 meters per second squared, that is the acceleration due to gravity. Note, the constant acceleration of free-falling objects is due to gravity. The a in the equations must be replaced with the appropriate value and sign for the gravity's acceleration. Okay, and on Earth, that's 9.8 meters per second every second. There are some problems if we're just trying to get an approximation. We might say 10 meters per second squared, but you'll know specifically when a problem wants to use that. Note, if the object is just released from rest, there's like no forceful throwing or pushing, then V initial equals 0 meters per second. This is really important to understand and interpret some of the word problems because they'll say they dropped something or just fell out of their hands. The initial velocity is 0 meters per second. So now let's try to get a little bit more quantitative view here. We are going to do approximations and get an understanding of what happens to an object in free fall as it goes upward and then downward. Okay? We assume up is positive and down is negative. The planet is important for vertical launches, vertical, up and down, launch, throwing it up. What is the acceleration due to gravity? 9.8 meters per second squared, and it's pointed towards the center of the Earth, so in our convention, it's negative. When an object is thrown straight up, the object's velocity gets docked by this amount every second. So if it's on the way up, you subtract 9.8 meters per second squared. On the way down, you still subtract 9.8 meters per second squared. On this page, we're going to round everything to 10 meters per second squared so we can do the problems in our head. So think of jumping on a trampoline. You start upwards really fast from the bounce, right? You go up and then you slow to a stop and then you start falling again downwards and go faster, faster towards the trampoline. So similar things happen when, for example, a ball is shot up in the air by this cannon. It has an initial velocity upwards of 30 meters per second. So that's a positive 30 meters per second. But we know the acceleration due to gravity is acting downwards, approximately 10 meters per second squared. So that means in 1 second, we're going to do a minus 10 meters per second here. So that goes down to plus 20. In another second, we do another minus 10 meters per second for this 1 second. So it goes down to plus 10. And by the end of the third second, plus 10 minus 10 meters per second goes down to 0. Anything that gets thrown up in the air and reaches the peak is going to stop only for an instant as it then turns around and starts going down. On the way up, all these velocities are positive. At the top, the velocity is 0. So at the top, the ball doesn't stop. It starts immediately falling downwards because the acceleration due to gravity doesn't get turned off when it comes to the top. The ball is just going to the top, slowing to a stop, and then must come back down. So in 1 second, it goes from 0, minus 10 meters per second in that 1 second, to negative 10 meters per second. Then the next second, it gets another negative 10 meters per second. So of course, now we're at negative 20 meters per second. Get another second going by, you've got another negative 10 meters per second. Let's note some symmetry here. On the way up, it went 30, 20, 10, 0. It was slowing down. On the way down, it speeds up. Negative 10, negative 20, negative 30, because it's going downward. But look, before 1 second, before reaching the top, after 1 second, after reaching the top, these are both at a magnitude of 10. 2 seconds before the peak, 2 seconds after the peak, the magnitudes are the same. So on the way up and on the way down, we see that at minus 3 and after 3, we are at the same magnitude. So what happens when you get to the top? At maximum height, velocity must be 0 because it's got to turn around. You're going in the positive direction, stop for an instant to turn around and go downward. When this object is moving 1 second before reaching the top, we noted the velocity was a plus 10 meters per second. And when it was 1 second after, that symmetry we were talking about shows you that it's at minus 10. Magnitude's the same. Now compare velocities 2 seconds before and after. Again, the symmetry of equal magnitude. So if you make a generalization by comparing the velocity at the same number of seconds before and after being at the peak, you will see that the magnitudes are the same, but the sign, the direction, plus and minus, is different. Plus on the way up, minus on the way down. What is the acceleration for every single instant that the ball is going up? It's at the top and going down. Every single instant, the acceleration of gravity is on at negative 10 meters per second squared. This page we're approximating. So how do we summarize this? Velocity changes every second. Velocity equals 0 meters per second when it's at the top in the y direction. Acceleration is constant the whole time. It's approximately negative 10 meters per second, or negative 9.8 meters per second. So on this page, we're going to do more of these kind of general approximations. Okay, we're going to approximate the acceleration due to gravity at 10 meters per second squared for Earth, and for Mars, 4 meters per second squared. Different planets have different acceleration. So now think of this. I drop a rock from the top of a cliff. How fast is it moving after 3 seconds? Well, dropping, you're just letting it go. That first instant, it's at 0. So your V initial is 0 meters per second. Your acceleration is negative 10 meters per second squared. They didn't say that you are on Mars yet. So now, for 3 seconds, you start off at 0. You go negative 10, negative 20, negative 30. You can do this easily in your head, and you could also use an equation. How about I throw a rock downward from the top of a cliff? The rock leaves my hand at 20 meters per second. It must be negative because I threw it downward. How fast is the rock moving after 2 seconds? Well, now V initial is a number. Throwing gives it an initial velocity. I threw it downward. Here's that negative. And for 2 seconds. So now, you see I have my picture. At the top, 0 seconds. I'm already going at negative 20 meters per second. And in the next second, I do a minus 10 meters per second. And in another second, I do another 10 meters per second. And you can even check your work using equations. Now look at this third one. We are throwing the rock upward. So where we had a diagram here where the ball starts at the edge of the cliff and is going to go down, starts at the edge of the cliff and goes down. Now we are at the edge of the cliff, but going upward first and then is going to fall downward. I throw a rock upward, positive direction. The rock leaves my hand at 40 meters per second. Okay, surely impossible. So how fast is the rock moving after 2 seconds? Well, think of it this way. It's plus 40 upwards. So after 1 second, I still have to subtract 10 and subtract 10 meters per second. So at 2 seconds, it's still flying upwards at plus 2 meters per second. After 4 seconds, I have to do 2 more subtractions of 10, and I'm going to get finally to 0 meters per second. So it took 4 seconds to get to the top, 0 meters per second. After that, it starts falling downward. And so now that's another 3 seconds, another 3 sets of 10, negative 30 meters per second. Now we're doing things on Mars. Let's evaluate what happens on Mars. Our acceleration is different. A falling object's speed changes by 4 meters per second each second. Still pointing towards the center of the planet. We say downward is negative. Let's keep that. So now I drop a rock from the top of a cliff on Mars. How fast is it moving after 3 seconds? Well, I said drop, so the initial velocity is 0. The acceleration on Mars was given to us as 4 meters per second squared, and we know it points downward, so we make it negative. And our time is 3 seconds. At time equals 0, we're at 0 meters per second. It's just a drop. And we keep on doing -4, -4, and -4 for the 3 seconds. And so you'll get to -12 meters per second. And again, you can check your work with an equation. But how about, again, one of these throwing a rock upward on Mars? The rock leaves my hand at 20 meters per second. How fast is the rock moving after 3 seconds? I'm throwing it upward, so it's a positive 20 meters per second. My acceleration downward is -4 meters per second squared, and the time is 3 seconds. So after 1 second, -4, -4, -4. After 3 seconds, it has slowed down to just +8 meters per second. Still moving upward, never reached the top. It would take 2 more seconds to get to the top and have a velocity of 0.